Hey guys, welcome back. We're going to get into the Chapter 4 review. We'll start off with number 6. Each month, a brokerage house studies various companies and rates each company's stock as being either low risk or moderate to high risk. In a recent report, the brokerage house summarized its findings about 15 aerospace companies and 25 retailers in the following table. Can be found on page 165, problem 413. So the first thing that I would do, which I've kind of advocated, is to make a contingency table out of the data that we have here. So I'm going to go ahead and do that. Okay. And this is kind of misleading here, so I'm just going to scribble that out. And we're going to put it in the center here, so 9 and then 10. Perfect. And then... okay. So some things that I would do is I would total up these columns right off the bat. And I think that's going to help us answer the problem. So we total up the low risk column. 6 plus 15 is 21. The moderate to high risk column, 9 plus 10 is 19. And likewise horizontally, 15 and 25. We see that the column 15 and 25 adds up to 40, and the row of 21 and 19 adds up to 40. So our total is 40. So now we can get into the problem, and I think kind of proceed a little bit easier. So A, the probability that the company is a food retailer. So that's just going to be the marginal probability of the or the marginal frequency of the food retailer over the total number of companies being looked at. So we'll just say probability of F is equal to 25 over 40. Sorry about that, guys. Had to take a quick pause. I noticed that Sports Center was on in the background, and you could probably hear that. So. Okay, so we just covered A. We got 25 over 40, which we do the math, and it is 0.625. We go on to B, the probability that the company's stock is low risk, so the probability of L. That's going to be the marginal frequency of low risk, which is 21 over the total of 40. So 21 over 40 is 0.525. We move on to C. The probability that the company's stock is moderate to high risk. So similarly, the marginal frequency, so over the total. So 19 over 40, which is 0.475. One thing you notice with B and C is they're complements of each other. So we could have defined the probability of moderate to high risk, P of M, is equal to 1 minus the probability of the low risk. And that would have given us the same answer. So that's just our complement rule. So we can define one of them as low risk, and then the other one is like not low risk. So then that would have just given us 1 minus 0.525, and then also given us the correct answer. Okay, and then we move on to D. The probability that the company is a food retailer and has a stock that is low risk. Okay, so we're going to find the intersection point. So we look at the low risk column, and we look at the food retailer column, and we see where they intersect. They intersect at 15. So the probability that something is food retailer and that it's low risk, and that's just going to be that intersect frequency over the total frequency. So 15 over 40 is 0.375. And then lastly, E. probability that the company is a food retailer or has a stock that is low risk. So this is probability of F or L. And we know from our addition rule for non-mutually exclusive events that this is going to be equal to the probability of F plus probability of L minus their intersection. So, and we've already calculated all those values, right? So 0.625 plus 0.525 minus 0.375, and that's all going to shake out to 0.775. So that's number 6. So we'll move on to number 7. So that was using all of our elementary probability rules. So part 7, or number 7, is using the above data. So if we randomly select one of the total of 40 companies, find the following. So we're going to look at A. A, the probability that the company stock is moderate to high risk given that the firm is an aerospace company. So we'll say the probability that it's moderate to high risk, so we'll just call that M, given that it's an aerospace company. And now we know our formula for conditional probability is the intersection, or the probability of the intersection, over the probability of that which is given. And so then we go up and we use our table to find these intersection points. So we see that the intersection of moderate to high risk and aerospace is 9. So in order to turn that to a probability, we say 9 over 40. And the probability of A is 15 over 40, which is 9 over 15, or 0.6, 60%. B, probability that the company's stock is moderate to high risk given the firm is a food retailer. So this is going to be very similar. Given that it's a food retailer, probability that it's moderate to high risk. We again do the intersection on top and the probability of the given on the bottom. And the intersection is 10 over 40. And probability of F is 25 over 40. 40s cancel out. We get 10 over 25, which is equal to 0.4. And then C, determine if the events, the firm is a food retailer and the firm stock is low risk, are independent. Okay, so this is kind of a separate question. But the easiest way for us to go about this is to check if the intersection is equal to the product of the two marginal probabilities. And we learned that in I think the second video lecture for conditional probability and independence of events. So the two things that we're looking at are food retailer and low risk. So we'll say probability of food and low risk is equal to question mark the probability of F times the probability of L. And we have all these numbers. So we know that probability of F and L is 0.375. We know from looking above that the probability of F is 0.625 and 0.525 for that. We multiply those together and we get 0.328125. And those are not equal. So because they're not equal, we say not independent. If they were independent, we would see that those are equal. Okay. On to 8. 8's going to be our Bayes theorem problem, and like I mentioned in the Bayes theorem video, if you would like to use Bayes theorem, go ahead. I am not going to teach you guys to solve problems using Bayes theorem because I think it's just much more simple to solve it using a contingency table, and so then that's how I'm going to do it. If you have questions on that, again, let me know in the discussion, and I can give you a solution using Bayes theorem, but we're going to go ahead and walk through it using a contingency table. A company administers an aptitude test for managers to aid in selecting new management trainees. Prior experience suggests that 60% of all applicants for management trainee positions would be successful if they were hired. Furthermore, past experience with the aptitude test indicates that 85% of applicants who turn out to be successful managers pass the test, and 90% of applicants who do not turn out to be successful managers fail the test. And this problem 440 on page 176 if you'd like to just see it in the book. Okay, so the first things we have to determine are what are our events, what are our variables here. And we can see that there is passing the test and being a successful manager. So that's how we're going to approach making our contingency table. I don't know what that is doing. Okay, so that's how we're going to approach making our contingency table. So on the left-hand side, we're going to put being a successful manager of S being a successful manager and S complement as not being a successful manager. And then I'm going to use T for passing the test and not T for not passing the test. And then the next objective would be, let's write down what we know. So we'll reread the important parts of the question. Prior experience suggests that 60% of all applicants for management trainee positions would be successful if they were hired. So don't be confused by the if they were hired part. That kind of gets thrown in there, I think, to confuse you. But so this would just say, regardless of taking this test, prior experience suggests that 60% of all applicants would be successful. So that's just probability of success, or being successful, of 0.60. The next thing, furthermore, past experience with the aptitude test indicates that 85% of applicants who turn out to be successful managers pass the test. So given that they turn out to be successful managers, they pass the test. So probability of passing the test given that they turn out to be successful managers is 0.85. And then next, and 90% of applicants who do not turn out to be successful managers fail the test. So the probability to fail the test given that you're not a successful manager is 90%. So we can read that again as, given that they're not a successful manager, there's a 90% chance that they failed the test. So the way that I like to approach this is I like to first write down what we know, in the table. So first thing we know is that the contingency table, this is a probability contingency table, the total probability is always going to be 1. Then let's write down the stuff that is in the table. So the stuff that's going to be in the table are marginal probabilities and intersection probabilities, okay, of which we only have one. We have a marginal probability. So the probability of success is 0.6, so we can put that here. And then we know using our complement rule that the probability of not success or not being successful is 1 minus 0.6, so 0.4. So now we have down in the table all that we know. The next step would be to use our conditional probability formula in both cases to find out what the rest of the table is. Before we even look at questions A and B, we want to just complete this whole table, get it out of the way, and then answer the question that is posed to us, because then we'll just have all of the information in front of us. So I'll first write down our conditional probability, and we know from the formula it is probability of T and S all over the probability of S. And then we can write down the other one as well. That's not T and not S over the probability of not S. And so then all we're going to do here is we're going to look and see what do we have. Because ultimately we're trying to solve for these intersections, right? So we look here and what do we have? We're given in the problem probability of T given S. We're given the probability of not T given not S. And we are given in the problem the probability of S, so 0.6. And we solved for the probability of not S. So in both cases, now we can solve for the intersection. So in this bottom one here, we're just going to multiply both sides by the probability of not S, which is 0.4, to come up with the intersection. So not T and not S. So we multiply 0.9 times 0.4, and that gives us 0.36. So we look to see where not T and not S intersect, and it's right here. Okay, and then we do the same thing at the top. We multiply through 0.6 to 0.85, and we get, what do we get? 0.51, and that goes in the intersection of T and S. And then we can just solve for the rest of the table. 0.6 minus 0.51 is 0.09. 0.09 plus 0.36 is 0.45. 1 minus 0.45 is 0.55. And lastly, 0.04. So we have the whole table done. So now let's just see what A has to say. That's not an at symbol, that's an A. If an applicant passes the aptitude test, so given that they pass an aptitude test for managers, what is the probability that the applicant will succeed in a management position? So this is asking us, given that they pass the test, what's the probability of success? So the probability of success given they pass the test. Okay, and then we would just write our conditional form out, which is the probability of S and T over the probability of T. Lo and behold, we have all of this information because we completed the table. So there's no guesswork, there's no confusion at this point. It's just plugging and chugging. Okay, so the probability of S and T, we calculated as 0.51. That's that intersection point. And then the probability of T is 0.55. And that shakes out to be 0.927 and some other decimals. And then B says, based on your answer to part A, do you think the aptitude test for managers is a valuable way to screen applicants for management trainee positions? Explain. And the answer is a resounding yes. It's yes because of those people who have passed the test, we know from this question that we just answered, almost 93% of them are successful. Whereas with the general population, just 60% are successful. So it's asking if the test is of value to us. It absolutely is of value to us, because if we only hired people that passed the test, then we know that we're getting roughly a 93% success rate on them being successful. But if we just hired everybody that applied, 60% success rate on them being successful. Okay, so that's how you would interpret that. And honestly, that's really the most important thing here. I mean, you guys are in a business statistics class. You wanna be able to crunch the numbers, but then understand the conclusions and the analysis that you're making. And this is why I don't mess with Bayes' theorem. I think Bayes' theorem just really confuses us, and it kind of gets us stuck in the math. I would rather us get the whole picture, be able to make a calculation based upon the whole picture, and then focus on, well, how do we interpret this? How do we analyze this? And answering B is really the important thing. Okay. So then we move on to there. So we move on to 9, and it is just construct a tree diagram for the situation described in exercise 4. And I actually believe I already did that in the lecture. So we'll just say, okay, already. Yeah, I did do that. So we'll go on to 10, and this will be our combinations problem. In poker, how many different ways can you make a flush if you are dealt a 5-card hand? What is the likelihood of making a flush when you are dealt a 5-card hand? So 2 things. They're asking us to count the number of combinations, and then they're asking us to tell what the probability of that is. So the first thing that we'll do is we'll count the number of hands. So the ways that you make a flush are obtaining 5 cards from all one suit. So there's 13 cards in one suit. So we could say 13, choose 5. Of the 13 cards in that suit, we're choosing 5 of them. So that's also equal to the other notation of 13, choose 5. That's not 13 over 5, that's just a different notation. You can use whatever notation you want, and yeah, that's that. So I'll go ahead and write this out. So that's our our formula then was large n factorial over little n factorial times large n minus little n factorial. So I'll just write that out. So we have 13 factorial over 5 factorial times 13 minus 5 factorial, which is 13 factorial over 5 factorial times 8 factorial, which 13 times 12 times 11 times 10 times 9. Times 9 times 8 factorial. That's going to be 5 times 4 times 3 times 2 times 1 times 8 factorial. We factor out the 8 factorials. And so we get 13 times 12 times 11 times 10 times 9 all over 5 times 4 times 3 times 2 times 1. And that is going to give us 154,440 all over 120, which is equal to 1287. And then the one thing that you'll notice is this is per suit, right? So this would be like clubs or spades or whatever. So in order to get the true number of combinations, we would just have to multiply this 1287 times the number of suits, which is 4 suits. And that's going to give us 5148. And lastly, we have to figure out the number of combinations of any 5-card hand, which is going to be 52, choose 5. And you can plug this into your calculator, or you can dole out the formula. but that's ultimately going to come down to 2.59896. So roughly 2.6 million. And so then the odds of obtaining a flush in a random 5-card hand is just going to be, we'll just say probability of flush is going to be the 5148 combinations over the total number of combinations possible. And that is going to leave us with 0.00198. So not very likely. Okay, guys, leave any questions you have in the discussion forums. Well, and till next time, I guess. All right, thanks so much. Bye-bye.